Hello, this is Mrs. Boots, and we're going to do our notes for our lesson on properties of quadratics. Now, some of this is going to seem like review. It's very, very familiar. Let's first look at the graph of the quadratic. There's key information that you can determine from a graph. For example, the place where the curve intercepts the x-axis is known by three different names. Okay? We call them roots. Actually, there's four names, right? Because there's x-intercepts, roots, they're called zeros, and they're called solutions. Because when I'm solving a problem, we're solving for x. So we're getting our solutions. The next piece of information we can get from our graph is our y-intercept. This is the place where the x value is 0. For our x-intercepts, y equals 0. So we'll just put a little note in here. X equals 0, y equals 0. Now notice we have this beautiful dash line running right through the middle. That dash line cuts the parabola in half because the parabola is completely symmetric. One side matches the other. And if I fold it on that line, I can line the two sides up. This line is called the axis of symmetry. Most of the time we abbreviate that as the AOS. Okay? The axis of symmetry always runs through the either highest point or lowest point on the parabola. This point is called the vertex. It is either a maximum or a minimum, depending. Now, in this case, since my parabola is upside down, think of it as the top of the hill. So at the top of the hill, I would have a maximum. If it were a ditch or a valley, it would be a minimum because it would be at the bottom. And that's the picture that's in your notes, is the right side up or facing up parabola where the vertex is a minimum. So now we're going to look at examples 1, 2, and 3. Notice all three of these examples are in the same form that we covered back in our parent functions unit. So this should be very, very familiar to us, all right? We're just going to start with the transformation. What can we identify? Well, the 2/3 is a stretch. Is it a stretch or compress? Right, it could be either one, but because it's less than 1, it's actually a compression. Okay? The 5 is going to move it to the right because we do the opposite. And the 7 moves it up. So I went right 5 and up 7. So if I drew a graph, that point right there is the new starting point. It went right 5 and up 7. Now, does this parabola face up or face down? It faces up. And the 2/3, think of it as a slope. We're going to go up 2 and out 3. So I'm going to go up 2, out 3. So my parabola is wider. Up 2 and out 3. Now, this point right here at the bottom is the vertex. Where was that point? Well, that point is at 5, 7. We went right 5, up 7, so it's at 5, 7. Easy enough. This is our vertex. Now, is it a minimum or maximum? Yeah, it's a minimum. So we'll just write min in parentheses so that we can identify that. Now the last step. What is the domain and range? Cool part for quadratics, domain is always negative infinity to positive infinity. The range, I'm going to start with my lowest y value. My lowest y value was 7. We're including the 7, and then we're going up. So it's going to go to positive infinity. Okay? This culminates all the properties. So we have some new terminology, right? Does this quadratic have any roots? No. It doesn't even touch the x-axis, so it doesn't have any roots. Does it have a y-intercept? Yes, it's off my graph, but but it does have a y-intercept. Let's look at number 2. Same thing, start with your transformations. Number out front, I notice it's negative, so it's going to reflect. That means this parabola is going to be facing down. It's a whole number, so it is a stretch. The 3 inside is positive, so it's going to move to the left. And the 8, because it's negative, moves it down. So on my graph, I'm going to go left 3, down 8. That is my starting point. That is also my vertex. Remember our starting point here? What was that point again? -3, -8. This is my vertex. We're going to label it on the graph. Now, is it a maximum or a minimum? Well, let's graph first. We're going to go down 2, out 1. So down 2, out 1. So is that a max or a min? Yeah, this one's a max because it's at the top of the hill. Because it's facing down, is it going to have any roots? No, there's no roots. Because it doesn't cross the x-axis, there's not going to be any roots. Now let's look at domain and range. What's the domain going to be? Negative infinity to positive infinity. And the range starts at the -8 and goes down to negative infinity. But remember, I need the big number first. So I'm going to write that as negative infinity to -8. And that -8 is going to have a square bracket because it's on the curve. Okay, last parent function example. What is the transformation? Well, I have a +3, so I know it's going to stretch. Then I have the -8, so we moved it down 8. Did we move it left or right? No. There's not a number inside with the parentheses, so it did not move left or right. So if I draw this graph, it's just going to go down 8 and stay right on the axis. So what is that coordinate? That coordinate would be 0, -8. That is my vertex. It's my new starting point. Now, which way is my parabola facing? Is it facing up or down? It's facing up. So I'm going to go up 3 over 1, up 3 over 1. Super skinny little parabola. Got nice and narrow because of that stretch. Does this one have roots? Yes, this one is going to have some roots. In order to find those roots, I would actually have to use factoring or quadratic formula. And we're going to do that later in this unit. For right now, I just want you to identify that this one has roots because it crosses the x-axis. What is the domain and range? You got it. Domain is infinity to infinity. And my range, this one's going to start at the -8 and go up. So I have a square bracket with my -8 going to positive infinity. Those are our first 3 examples. Example 4. So now we're going to take a step. We're going to take our picture and look at the table. Remember, on the calculator, you can do that. Instead of doing graph, we can do second graph and look at our table of data. It's the same information, just in a different format. So let's identify the same key pieces in this format. So my roots. My roots are where y equals to 0. So I have a root here at 0, 0, and I have a root at 6, 0. Now remember, the maximum or the minimum is going to be the highest or lowest point. So what's highest, the x or the y? It's the y value. So in this case, is it going to be a maximum or a minimum? Let's look. I see my y's, because remember, x's are my independents, and y's are my dependents. Okay? So my time is x, my height is y. My time is independent, my height is dependent. So let's look at the height. It goes up, 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 comes down, down, down. Okay, so that means I'm going to have a max. What's the highest y value? The highest y value happens right here at 40. So this would be my vertex or my maximum. Either way. Now, based on that information, we can paint a picture or discover the facts concerning something. So this could be a football, this could be a missile, it could be a bottle rocket, it could be anything, okay? So they asked for the max. When they asked for the max, they're looking for a y value. What was the highest y value? 40. Then I believe the units are feet, okay? Make sure you always include the units. Now, what's the time at that maximum? So here I would look for my x values. Okay, my time is 3, and it's in seconds. All right? Now they ask for the landing time. How do I know it lands? Okay, well, let's think about this. How high is the ground? Well, the ground is at 0. I know, that's assuming we're at sea level, but that's okay. Even if you're in Colorado, you throw the football, it's not going through the ground into the earth until it reaches sea level. So the ground is essentially 0. Where is my landing? Well, it's going to be either the first one or the last one. Based on time, however, it's going to be the last one. That's my landing. As I've thrown the football, it's got to land. That's the furthest one away. So my landing time, the x value, is 6 seconds. Now this one's a tricky one. How long is it above 35 feet? So let's find 35 in our y's. I have a 35 at 2 seconds and a 35 at 4 seconds. So at 2 seconds, it hits 35, goes above it, and comes back down at 4 seconds. So 4 minus 2 equals what? Right, 2. Super easy. So it's above 35 feet for approximately 2 seconds. Now, yes, I know, we don't want to equal to 35 feet, so we got to play with it there. Now, domain and range. Remember how I said a quadratic always has a domain of infinity to infinity? Okay, maybe not always. Mathematically speaking, yes, it's going to have a domain of infinity to infinity. But in real life, that football does not go through the ground, through the planet, and keep going to infinity. It stops. So we have to put our real world stop points. What are our limits, okay? We cannot go backwards in time, okay? So there's no negative time. No time machines. Sorry, this is not a sci-fi movie, okay? No negative time. And you also don't go through the ground. So we're not going through the ground. And you say, well, miss, what if it's a mud puddle and it hits the puddle and sinks to the bottom in the mud? Technically, it's below 0. Okay, just stop. All right, we're not taking those cases right now. If you want to do the missile that goes underwater, we'll do that in a future problem. Okay? We cannot have negative time. We're not going to go through the ground. So my x's and my y's have to be what? Positive. So I'm looking at the domain just in this table. What's my lowest x? 0. So I'm going from 0 to my highest x, 6. Okay? Now let's look at the range. It goes from 0, that's the bottom. What's the maximum height? 40. So that would be my range. Notice there's no infinities when we're doing real world problems. Okay, examples 5 and 6 would give you the equation. You have to figure out the table. Well, that's super easy, right? Because we can just take that equation and plug it into y equals. No big deal, okay? My x values are my time. My y values are my height. Super easy. So we plug it into y equals and we get a table. Don't write the whole thing down, okay? We start at 0, 0. Why do we start at 0, 0? Because we cannot have negative time, okay? Now I'm going to scroll down until I see the highest y value. I'm looking for that highest y value. So I got really close, and at 15, it said 4080, so 4080. At 16, my y value was 4096, and at 17, it went 4080. And then at 32, it went to 0. Okay, so I'm just going to write those points down. Now, what does the problem ask me for? For this function, what is the maximum height and how long does it take for the rocket to land? So I want my max height and my landing. Okay, so is the max height going to be x or y? Max height is y, okay? So I'm looking at my highest y value. What is my highest y value? 4096. And that's feet, okay? Now landing. When does it land? When it hits the 0 again. Landing is the x value, and that's going to be 32 seconds because they said time was measured in seconds. Okay, how many seconds until it lands? We're going to do the exact same thing on number 6. It's a different problem, but that's okay. In this one, we have a water slide modeled by an equation. So we're going to plug that equation into y equals. Yes, x is still time, and y is going to be, yes, the height. Okay, so we have time, our independent, and height, the dependent. Now, scroll through the table. At 0, because I can't go backwards in time, no negative time, what's my height? 120. Okay. At 1, it goes down to 119.5. So, it's going downhill. At 59, my height is 3.5. So I'm 3.5 feet above the ground. And at 60, my height is 0. That means I landed in the splash pool or on the ground in the playground. Since this is a water slide, I'm going to assume it's a splash pool. So what was the max height? Yeah, it's at the very start. Now, even if it went higher in negative time, remember, we still start with 0. So my max height, which is my y value, is 120 feet. My landing in seconds is where the y is 0, and x is going to be 60 seconds. So that water slide lasted a full 60 seconds. That's a pretty long water slide. Example 7. Now I have a different form of my quadratic. Notice there's no parentheses in example 7, 8, or 9. This is what we call standard form. Okay? Standard form means that there's certain information we can see, but it also means that my exponents are written in descending order. I have x squared, x, and then my constant. So in standard form, there's pieces of information we can just look at it and see. We don't have to do any math, no calculations, which is beautiful. There are two things. The A. The A is always in front of x squared. So my A is something I can just look at it and see. A in this case is -2. So that means my parabola is going to be facing down. Now the second piece of information we can look at and see is the y-intercept. The y-intercept is always the C value. It's the constant. My constant in this problem is 10. So my y-intercept is at 0, 10. Well, let's think about this. If I plug in 0 for x, I would have 0 plus 0 plus 10. That would give me my y-intercept of 10. That is what we can look at and just see. We don't have to do calculations. But we can still find the axis of symmetry, the vertex, and the roots. So let me show you how we do that. The axis of symmetry has a little formula. That formula is negative b divided by 2a. Okay? Negative b divided by 2a. So let's look at that. What is b? b is 8. So I'm going to take negative 8 divided by 2 times a, which is negative 2. Okay, let's simplify that. So negative 8, and this is negative 4. So what's negative 8 divided by negative 4? Positive 2. So my axis of symmetry is a line at x equals 2. That is cutting my parabola in half. The cool part is the vertex. The vertex, I'm going to take my axis of symmetry that I just found, negative b over 2a. And then I'm going to plug that x back in and find the y. Okay? That's how we find our vertex. So, I know it's a 2. It should be exactly identical every single time. Axis of symmetry and the x value should match for the vertex. Now, let's find the y value. So we plug it in. What have we got? This may be a bit tricky, right? So I'm going to take, I'd have negative 2 times negative 2 squared, times positive 2 squared, plus 8 times 2 plus 10. That's what I would plug into my calculator because I'm plugging in that x. And what do I get? I get 18. So my vertex is at 2, 18. Easy enough. This paints a picture because if I do my graph, I put my axis of symmetry at x equals 2, dash line. I go to 218, I put a dot. I go to 0, 10, I put a dot. Now I can start framing my picture. The roots are the tricky part. In order to find the roots, you either have to factor or use another form of solving. For these problems, we're going to factor. That's why we went back through all of those factoring. Okay, so I have to take that and factor it, right? All right. Well, I noticed that all 3 of these are divisible by 2. Actually, negative 2. So I'm going to pull a negative 2 out, and I'm left with x squared minus 4x minus 5. Okay? So remember, it's a simple factor because the number in front of x squared is 1. That's awesome. So I need 2 numbers that multiply to give me 5. I know, real anticlimactic. So that's going to be a 5 and a 1. X is up front, 5 and 1 at the back. The bigger number gets the same sign as the middle. But we're not done. Now, is there an x with that negative 2 out front? No. Is there an x inside this first parenthesis? Yes. So set it equal to 0. X minus 5 equals to 0. Solve for x, I get x equals to 5. So one of my roots is at 5, 0. Okay? Let's take the second parenthesis. Does it have an x at the front? Yes, it does. X plus 1 equals to 0. Move the 1 over by subtracting it, and x equals negative 1. So my other root is at negative 1, 0. So I would put the dash line, a point at 218, a point at 210, and a point at 50 and negative 10. And then you connect the dots to form your parabola. Let's walk through 8 and 9, and we're just going to find our wonderful parameters. Okay, the a and the y-intercept are the easiest, so let's do those first. A is in front of x squared, so that's a 1. Easy enough. Y-intercept is the constant at the end. Well, that would be 4. So my y-intercept is at 0, 4. Now let's calculate. Axis of symmetry is negative b divided by 2a. But there isn't a b. That's okay. So we have negative 0 divided by 2 times 1. I know, it's 0, right? So at x equals 0 is where the axis of symmetry is at. Now we plug it back in. The vertex, I'm going to take my 0, plug my 0 in here. What do we get? Yeah, 0 squared plus 4 is just 4. So my vertex and my y-intercept are the same. Okay, that's fine. We can do that. Now let's look for the roots. Here's the problem. Most people try and do difference of two squares. Is this sign mean difference? No, because a difference would be a subtraction symbol. So I'm going to solve this a different way. I'm going to take x squared plus 4, set it equal to 0. Because remember, to find the roots, y has to equal 0 every single time. Okay? I'm going to move the 4 over. So I have x squared equals negative 4. Okay, that's interesting, but all right. How do you get rid of a square? You take the square root. So now I have x equals plus or minus the square root of negative 4. Whoa, that's okay. We can do this. You're getting ready to learn in another lesson that this is actually possible. So we're just going to put a box around it. You could go ahead and take the square root of 4 and get 2, but we're going to leave it the way it is. That would be my roots. So now I have information. What does this mean? This means it doesn't touch the x-axis, okay? This was like our case where it doesn't touch the x-axis. It actually is pointing up and it's sitting above the x-axis. But that's okay. We can handle it. Example 9. A. All you gotta do is look. Where is it at? In front of x squared, okay? The b is in front of the x. C is the constant. If it's not there, it's a 0. No big deal. So what is A? A is 3. Easy enough. Y-intercept. The y-intercept is the C. C is 0. So my y-intercept is 0, 0. That's the stuff I can look and see. Now, let's look at the stuff we're going to calculate. Axis of symmetry. Negative b over 2a. Put a big yellow box around it, or purple box, or whatever your favorite color is. Make sure you know how to find these things. Axis of symmetry, negative b over 2a. So I have negative, what's b? 6 divided by 2 times 3. Well, that's just negative 6 over positive 6, which is negative 1. So at x equals negative 1, I'm going to have that vertical dashed line that's cutting my parabola in half. Now let's look at the vertex. Remember, the x value comes from the axis of symmetry. Now I just have to find my y value. So how would we do that? Okay, so I've got 3 times negative 1 squared plus 6 times negative 1. Well, negative 1 squared is positive 1. So that would just be a 3. And 6 times negative 1 would give us, negative 6. So it's going to be a negative 3. No big deal. Okay? Now to find the roots, we need to factor. Okay? What can we pull out? We have a GCF here, right? Because I have two x's. I can actually pull out a 3 with an x. When I do that, I'm left with x plus 2. Remember, you're setting an equal to 0 to solve for x. Does the 3 have an x with it? Yes. So we have to set it equal to 0. Does the part in parentheses have an x? Yes. Set it equal to 0. Okay? First part, 3x equals 0. Divide by 3's. X equals 0. So one of my roots is at 0, 0. Well, we already found that. That's the cool part about 0, 0. It's a 2 for 1. If it's a y-intercept, it's also an x-intercept. You automatically know that they're the same. Now, the x plus 2. Subtract the 2, and I get x equals negative 2. So my other root is at negative 2, comma 0. So I would put all of that information on the graph and draw my parabola. This concludes all of our notes for properties of quadratics.